This is J. Sravana working as Assistant Professor in AC Department. Today's topic is we are discussing about microprocessor and microcontroller. So before discussing the microprocessor and microcontroller, first we need to know what is meant by microprocessor. So if you see, a microprocessor is a combination of micro as well as a processor. So micro means what? It's you can say 10 power minus 6. So you can say a processor, what is a processor is nothing but it executes all the instructions like a CPU, you can say. And these the instructions which are executed in CPU are done in terms of microseconds. So that is what you can say, it is a more faster. So microprocessor, you can say it performs all the instructions in microsecond. And let us actually come under the definition of microprocessor. So what is the definition of microprocessor? You can say a definition of microprocessor is a controlling unit or else a CPU, which is designed in a very small scale integration, IC you can say, so which performs all the arithmetic operations, and it can communicate with the external devices which is connected to it. So that is what actual definition of a microprocessor. So you can come, you have various microprocessors like 8085, we have already discussed 8086, 8085 microprocessor, and the advanced, the next version is 8086. So today we'll be discussing the 8086 microprocessor, the characteristics of it, as well as the features, and what are the pin configuration, and what is the internal architecture. That is what the topic which is covered in this. So here we have already discussed what is meant by microprocessor. So it's a controlling unit or a CPU. And if you come across the characteristics, so what are the characteristics? So how you can define a microprocessor is more faster, that is you are saying it operates in microsecond. So what are the characteristics which depend on this microprocessor? The first one you can say, it's a data bus, width of the data bus. So the width of the data bus defines you how many bits a data bus can carry, or how many bits a data bus can be executed by the microprocessor. How many bits can be executed by the microprocessor defines you the width of the data bus. So suppose in 8086 you are saying it's an 8-bit processor. It means this is 8085. Right. So 8085 is an 8-bit processor. It means it carries, the data bus carries an 8-bit. So it can process only 8-bit. So now if you come across the 8086, it's 8086 is a 16-bit processor. It means our data bus carry 16-bit. Right. So this is how the speed can be defined. Depending upon how many bits a data bus can carry, depending upon that you can say the system is faster, the CPU is faster. That is the first characteristics of the microprocessor, that is width of the data bus. The next will come across, what is the next one is will come across the width of the address bus, width of the address bus. So this is another very important characteristics, where this address bus defines how much maximum memory it is acquired by the 8086 processor or the microprocessor, whatever you are learning about. So you can say example like 8085 has 16 address lines, right? Whereas 8086 has 20 address lines. So this gives us, this address lines defines you how much memory is assigned for my microprocessor, right? So the address bus, like example I'm going for 8086, it is having a 20-bit address lines. So you can depict how much the memory can be is 2 power 20. right? The 2 power 20, this 20 defines you the number of address lines, which gives you approximately 1 MB memory, right? So, what is the use of address bus is what? We can go for how much maximum memory it is acquired by an microprocessor, right? And next one is input and output addressing. So here, when as I said, a microprocessor is nothing but it's a controlling unit, and it can communicate to the external devices which is connected to it, right? So here, IO addressing. IO addressing is nothing but input output addressing. So how many ports does a microprocessor have? Depending upon that, you can access the external devices. That means how many accessing the external devicing can be accessed by my microprocessor is also another characteristics for our microprocessor, right? So these are the three characteristics. One is width of data bus, the second one is width of address bus, and third one is IO addressing port, right? So, so you can see a microprocessor is an enhanced version of 8085, and it was designed by Intel in 1976. And it is a 16-bit microprocessor having 20 address lines and 16 data lines, right, which provides 1 MB memory. As we have discussed the characteristics, so 8086 have 16 data lines and 20 address lines, where 20 address lines gives you 1 MB memory. And it consists of powerful instructions. What is a powerful instruction? So, in order to operate any operations, as we said, a microprocessor is an ALU device. So, ALU means what? All the arithmetic and logical operations can be done. How those arithmetic and logical operations are executed? By giving some instructions. So when we are giving some instructions to my microprocessor, according to the instruction, whatever we have given, that will be executed. Either it may be a addition operation, or either it may be a subtraction or multiplication, or any logical operations. So one of the greatest advantage of this microprocessor is, at 8086 microprocessor is, it's have a powerful instruction set. So it means it is very you have a more number of instruction sets, where you can write instructions for different applications what we want in a very easy manner. And the another advantage is, the 8086 microprocessor works in two modes, that is a maximum mode and a minimum mode. So what is a maximum mode and minimum mode? So you can see I have a microprocessor, right? So for this microprocessor I need to interface the external devices, right? So whenever my microprocessor is working in maximum mode, you can say my microprocessor can work with more number of external devices, with more number of multiple processes you can work with. That is what a maximum mode. So maximum mode is suitable for the system having multiple processes which are connected to our processor. So what about the minimum mode? So if you come across the minimum mode, in this minimum mode, only one single process functioned. So means only one microprocessor which you are functioning is used. So that are the two modes which are supported by an 8086 microprocessor. So here, here there is another feature of our 8086 is the instruction queuing. So what is an instruction queuing? So instruction queue is nothing but the instructions which I need to execute are placed in the proper fashion, one after the other, to make my execution, to make my ALU faster. So what is a instruction QE? Instruction QE is a QE kind of thing. QE is nothing but where it have a sequence, right? So in the sequence, my instructions are placed one after the other before itself. So before, if you are placing my instruction, it means my processor can take the data and process it faster in a lesser time. So that is what the need of an instruction queue. So here our instruction queue is capable of storing 6 bytes. 6 instruction byte, which makes our processing faster. And next, so we have a 16-bit processor, and we have a 16-bit ALU, and we have a 16-bit register, internal data bus, and 16-bit external data bus, resulting in a faster process. So here we have another advantages, that the frequency of operation of my 8086. So in 8086, microprocessor can work in three versions of frequency. One is 8086 in 5 megahertz, 8 megahertz, and 10 megahertz. So these are the three frequencies where my 8086 microprocessor can work. And so this the next what is the another point is a pipelining. So what is actually a pipelining? So you, as you know, a pipelining, the name itself says you have a water flow in a pipe. It means we are showing a path for a water to flow via some a pipe, whatever you're using. Similarly, so I need to execute the instructions which are present in my microprocessor, in the memory. So how you can execute this? By a sequence. So step by step, we are placing in an instruction queue, and then you're sending it to the execution unit according to the control signals, and it is executed. So how it is done? What is a sequence? So you're making the instruction in the sequence. So that sequence is called as a pipelining. So how the pipelining is executed is by fetch stage, execute stage, and this fetch and decode and execute. Actually, we have fetch, and next one is decode, next is execute. So first fetch and the name itself, the meaning itself says as we are fetching, you're taking the instructions which I need to execute. So we are from the memory location where my instructions are present, I'm taking that, I'm fetching that, and I'm decoding it. Right? What is a decoding? It is converted into a machine level language like binary ones and zeros, and then it is executed by my ALU. So this is an actual sequence that is called as a pipelining, which is followed by an 8086 microprocessor. So here, what is a fetch? As we said, in an execution unit, as we said, we have an instruction queue which has a 6 bytes. So from the 6 byte queue will fetch the instructions one after the other and will execute. And execute stage executes those instructions. And what is another advantages? We have 256 vector interrupts. So we'll see what is an interrupt. Actually, the general meaning of interrupt is nothing but the stop the present execution. Stop the present execution, which is done by microprocessor. right? So we have as we are going for a multitasking kind of thing, multitasking, that is nothing but my microprocessor is communicated with the external devices. I need to work with more external devices. It means that I can go for more number of devices executed to it. Then we require we have an interrupts in between whenever my microprocessor is executing. So like that we can say we have 256 vector interrupts. Next, and it consists of 29,000 transistors. So as we have seen what is a microprocessor, right, and we have seen what are the features of my microprocessor. So, what is an actual difference? What is a comparison you can define with my 8085 and 8086? So, presently I'm going for 8086. So, why we are moving it into 8086? So, what is a comparison which you go for an 8085? So, you can see the size. First, the main thing is the size. 8085 is an 8-bit processor, and whereas 8086 is a 16-bit processor. And next, the address bus. So you can say address bus is 8085 is a 16-bit address bus, whereas an 8086 is 20-bit address bus. And next, the memory. So the memory of an 8086 can access up to 64. As we know, 2 power n is nothing but number of address lines. So how many address lines we have? 16 address lines. So 2 power 16 gives you 64 kilobytes. Right? So whereas if you go for 8086, we have 20 address lines. So 2 power 20, 2 power 20 gives you 1 MB. So this is what memory capacity by determining how many address lines. So the next, instruction. So instruction in 8085, you don't have a QE. So what is the instruction QE? We already discussed. What is it? We are placing the instruction before itself. It means for my microprocessor, it can execute faster before the instructions are placed before itself. So there is no need to search for my microprocessor going into the memory where my instructions are present and taking those instructions. So that part is removed. So that means you're having a very less number of less time, you can say very you have instructions placed before itself where it can ALU unit takes the instructions and execute faster. So the time is very less taken for the execution. Whereas if you go for an 8086, it does not have any instruction QE. So compared to an 8086 processor, you can say 8085 is slower. Next, the pipelining. So you can say as the instruction queue is not present in our 8085, the pipelining process is not supported by 8085. Whereas 8086 supports the pipelining process. Next, whenever you are looking about the IOs. So as we have said, according to the characteristics, we have an IO input and output address ports where you can connect you can communicate the external devices to my 8086 processor. So here in 8085 processor, you have it's an 8-bit processor, so 2 power 8, it gives you 256 IO ports. Whereas if you go for 8086, it can access about 65,536 IO device. That is 2 power 16 data lines which you have. Right. So the IO, how many bits the IO addressing can be depicted by the how many bits it can be accessed, right? 8085 access 8 bit. So you are writing as 2 power 8 bits, we have 256 IOs. Whereas if you go for the 8086, you have 16 bit, it is a 16 bit processor where it can answer 65,536 IO devices. And next we come across the cost. So the cost is very low, as we are not having any external devices which are included like 8086 instruction QA which is present in. So that is one example which I'm taking. So the cost for 8086 85 is low and 8086 is high. And let us now come across the architecture of an 8086. So, what is an architecture? So, architecture name itself says it's an internal block diagram which is present in an 8086. So, as we are saying, we are giving some instructions. We are taking the instructions are sent into the memory, and those are taken and those are executed in a ALU. So, in a words, you are saying you're giving an instruction, you're processing in an ALU, you are getting the output. So, how that path is formed? So how that path is nothing but how from where the instructions are taken. From there, how it is how the instructions are placed, in which memory it is placed, and from that how you are sending it to an execution. That path can be seen by the architecture of in 8086. So you can see my architecture of an 8086 is divided into two blocks. One is bus interface unit, one is execution unit. So bus interface unit, that is a BIU unit, and execution unit is EU. Right. So, why the division is done? So, in order to understand in an easy way, we are dividing my architecture into blocks, that is interfacing section, and another one is an executions section. Right. So, here we have a memory. So, memory interface, that is nothing but we have a ROM, RAM, right. So in this my memory, in that memory I've placed my instruction which I've executed. So we need a path where from the memory I need to send it into ALU unit in order to execute, right. So how it is sent? So by using the interface of execution, bus interface unit. So actual bus interface unit, the name itself says that it acts as an interface between the memory as well as the execution unit. So we need something, a mediator, where I can carry my instructions to my ALU unit. So that is that is done by the bus interface unit. So bus interface, you can see here you have a buses, a C bus, you have an instruction QE as we have discussed, which is a 6-byte QE, right. And we have some segment registers, ES, CS, SS, DS, and IP. We'll look after this individual in detail in the later slides. And we have a B bus here, where you have a summation symbol, where my from the memory interface unit I'm sending my data into the segments, as well as I'm sending the data to my instruction QE via C bus, which is placed one after the other, where this step-by-step instructions can be sent to my arithmetic logical unit via control unit, right. So you can see you can see a bus interface unit which consists of buses which interface between, which act as a mediator or a path between a memory interface as well as execution unit, right. So we'll see in detail later, right? Execution unit. So what is actually a execution unit? You can say the name itself, execution means we are executing, we are uh, adding some you're adding some numbers, you're multiplying some, we are operation is done. Execution means an operation is done. So in order to do some operations, what we require is an ALU. So the basic thing which is present in an execution unit is an ALU, right? Arithmetic logical unit, where this perform all the instructions which are given to it via a bus interface unit. So execution unit executes the instructions which are present in the instruction QE. You can say it's a 6-byte QE, right? So each instruction is sent to my arithmetic logical unit via the control signal, and it is executed, and you are sending the output. Right. So you can see in an execution unit we have a registers. So as we know, what is a register is a temporary storage. Right. So we have AL, AH, which is a 16-bit, and BH, BL. So L indicates it's a lower byte, lower 8-bit, and H indicates higher 8-bit. Right. So the overall each register is a 16-bit register, where you can use it as a lower 8-bit and higher 8-bit. Like that, we have you can say AX, you can say X indicates it's a 16-bit, and it can be divided into AL as well as AH. And another one is BL, BH, that is nothing but BX register, and CL, CH, that is nothing but CX register, DL, DH, that is a DX register. So these can be called as a general purpose register, right? General purpose registers, which are we are having a 4 general purpose register which is of 16-bit, and another we have, and next SP, BP, SI, and BI. These are the special purpose registers, right? So SP is nothing but the stack pointer, and BP is nothing but the base pointer, SI is nothing but source index, DI is nothing but a destination index. So these are the special purpose registers which we have. And coming across, we'll see in detail. And another section you have an arithmetic logical unit which is used for the execution, and another one is a flag register. So what is then actually a flag register? So what all the operations which are done in my 8086 microprocessor, it may be any instructions which are executing. It may be addition, subtraction of any kind, incrementer or decrementer, or a mod kind of thing, a counter. So all these, whenever you're executing, there are some points where you have an overflow, right? You have some zero flag, zero answer when maybe a zero, right? You may get a carry if you are adding any 2 bits. So like that, what status of my arithmetic and logical unit, what all the operations which are performed, that status can be defined by my flag register. So in detail, we'll see how many flags we have. We have a conditional flag and control flags. We'll see later. So this is a flag register. So how many bits my ALU can access is 16-bit, right? So my flag register status shows you a 16-bit. It's a 16-bit register. My flag register is a 16-bit register which shows you the status of the 16-bit which is processed by an ALU, right? So this is a overall architecture where we have an interface unit, we have that is bus interface unit, we have an execution unit, and in detail we'll see. right? So what is what? So you can say my architecture of an 8086 is divided into two blocks, right? Bus interface unit and execution unit. So we'll see in detail for each execution unit and the bus interface unit. So first, let us see the execution unit. So, what is an execution unit? So, execution unit gives instructions to a bus interface unit stating where to fetch the data and then decode and execute those instructions. So, its function is to control the operations on the data using an instruction decoder and ALU. So execution unit has no direct connection with the system bus, right? Everything is done via a bus interface unit. And next, what is a bus interface unit? So you can say bus interface unit takes care all the address and data transfers on the buses for the execution unit, like fetching the data from the memory and or taking the data from the ports, or writing writing the data into the port, or reading the data into the port. And it shows how the execution unit direction, and direction where my like read is sent and write operations are sent, right? So those are those are shown by a bus interface unit. And next, so we have segments, right? So you can see this is a CS code segment. You can say DS is a data segment, and SS is a stack segment, and ES is an extra segment, right? What is a segment? So our memory, how much memory we have? 8086 is having a 1 MB memory. That 1 MB memory is divided into um, segments, this is a 1 MB memory. Each of how many bit is 64 kilobyte. So why my memories are divided? What is the use of making my memory segmentation? So what is a memory segmentation? Is dividing my memory into several blocks, like a code segment, a data segment, stack segment, and extra segment, right? So each of how many? 64. So what does it use, right? So you can say example. I can say one example. So I have written a code for any you can say a traffic light signal, or else a counter program I have written, right? I need to execute it. So now I've already placed in my memory. So in which memory I need to place? So we are discussing the memory segmentation. So why the memory segmentation is done? So I'm taking some example. So I have written a program for a counter. So counter which counts the delay of 60 seconds, right? So what I need to do, I'll write some program, right? A code I'm writing for in order to generate a delay. So I need to place in the memory. So when my processor needs to work with this code, what my processor does, it goes to the memory where my code is present. It searches where my the counter program is present, right? So in order to search, and until the code which is present in my memory, until it finds that code, it goes on searches, right? It goes on search where my counter program is present, right? So what is happening there? There is a time it is taken for execution. So there is some delay for that execution, right? So that what is happening, my microprocessor will gives you uh, output will be delayed for this execution of my delay program. Right. So instead of that, what I'm doing is according to the application, according to the application, whatever you want. It may be the code which you are writing, right, or either the data which I need to access, right. So, or apart from this, the extra data which I need to access for my future purpose, I can store it. So I'm dividing my memory into sections where I can take my code in that memory location directly. So, if I'm writing a code for delay in a code segment, my processor knows my code which I need to execute is directly present in the code segment where I can fetch it directly. Right. Or my microprocessor need to execute some data which is present, so that data can be stored in some memory location that is present in the data segment. Right. So, my processor, we are saying to my processor before itself that data will be present in the data segment, and the code which I need to execute, which is present in the code segment, and stack related operations which I need to access, it can be present in the stack segment. And the extra content which I need to store for the future purpose, or which I need to execute it later, can be present in the extra segment. So what is happening here? The searching time for my microprocessor is reduced. So my microprocessor knows the code is present in the code segment which I need to execute, the stack which is present in the stack segment, which I can take it and execute. So before itself, whatever the content related to it, it is already stored in the related segments, related memory locations. So it makes my processor to function more faster, right? So that is what the memory segments are. Memory segment is nothing but we are segments are nothing but my memory is divided into blocks, segments, right? Each of code segment, you can say data segment and stack segment and extra segment. So this all comes under the 1 MB memory which I have. Right. So you can see here what is a code segment. CES again. It stands for a code segment, and it is used for addressing a memory location in the code segment of memory where the executable program is stored. Right. I said the code which I need to execute will be stored in the code segment. And data segment. So DS is nothing but what? A data segment. It consists of data used by the program and is accessed in the data segment by an offset address or the content of the other register that holds the offset address. And next one, the stack segment. So SS is nothing but a stack segment. It handles the memory to store data and addresses during the execution, stack related operations. And ES is nothing but the extra segment. So this is an additional data segment which I have, which is used for the string operations, for the extra destination data. String operations, you can say I have some data, string data 1, 2, 3, 4, 5 in some memory location like 2000. So this is stored by some registers like SI, and this this data string of data which is stored in the memory location 2000. I need to store the in 2000 we have 1, in 2002 in 2001 you have 2, in 2002 you have 3, in 2003 you have 4, in 2004 you have 5. So this data I need to transfer to some other memory location which is having an address location of 3000. Right. So like this, whenever I need to transfer a data from one memory location to another memory location, you can use this extra segments. So the next one is instruction pointer. So what is an instruction? what is an instruction pointer? So instruction pointer, it's a 6-bit register. So actually, what is meant by an instruction pointer? So in my memory location, I have a program where I have some set of instructions like 1, 2, 3, and 4, right? Which is having some memory location of 2000. Right. So I need to execute this program which is present in 2000. Right. So when my processor is executing first instruction, we have an instruction QE where my instruction, the second instructions which is placed in an order. That is what you have calling as a pipelining, right? So my instruction which I need to execute, the next instruction which I need to execute will be stored in my instruction pointer. So instruction pointer is a 16-bit register which holds the address of next instruction to be executed. So which makes my process faster execution, for my faster execution. Next, ALU. We have another part. ALU. What is an ALU? ALU is an arithmetic logical. It handles all the arithmetic and logical operations like plus, minus, multiplication, and the logical operations. Next, a flag register. As we have discussed, the flag register which is present in the execution unit, which stores you the status of my ALU. So here a flag register is a 16-bit register. So a general flag register is a basic flip-flop. Right, it will set and reset according to the status of my ALU, and it changes the status according to the result which is present in the accumulator, and it has 9 flags which are divided into 2 groups. Right, so you can say by default any of the instructions which is executed by my 8086 microprocessor will be stored in an AX register by default. So here we are having a 9 flags where it is divided into a conditional and a status. So we'll come across the conditional. So here in conditional flags we have first a carry flag, right? Carry flag is nothing but suppose indicates an overflow condition for an arithmetic operations. Like suppose we are adding 2 16-bit, right? So you can say I'm taking a 2 16-bit, or like example I'm going for as I'm having 5, 2, and 3, 4. So let us write the binary of this. So in a 16-bit, you can write it as 0, 1, 0, and 2 is 0, 0, 1, 0, right? And 0, 1, 0, 1, and 4 is 0, 1, 0. Right? Or else if you take this has, so here you can see if this is 1 nibble, 4 nibbles, this is another 4 nibble, right? So whenever you are adding this 4 nibbles and this 4 nibble, here the at last if you get a carry like this is 0, this is 1, this is 1, this is 0, this is 1, this is 1, and this is 1. Suppose in case here you have here you are having 1, 1, right? So here 1, 1 indicates 0 with the carry 1. So 0 with the carry 1 is apart from the 16-bit. The extra, this is a 17th bit which we have. Right. So this 17th bit indicates a carry. Right. So carry flag. It is nothing but it indicates it's an overflow. Overflow means what? Actually, whenever you are adding two 16-bit, the resultant will be a 16-bit. But here you are having an extra bit, the 17-bit, that is 1. right, at the end after adding. So this 17 bit indicates there is an overflow. So that bit is called as a carry flag. Next, auxiliary carry. So what is an auxiliary carry? So when an operations like arithmetic and logical, as I have taken an example, from the lower nibble to upper nibble, if you are getting a carry, that means that that carry is called an auxiliary carry. Like you can say, I'm taking an example. So I'm taking an example in order to indicate what is an auxiliary carry. So this is having, this is a 4 bit, this is another 4 bit which we have, and this is another 4 bit which you are going to have, and this is another 4 bit which you are going to have, right? So this 4 bits are called as nibble, and this 4 bits is called as another nibble. Right. If you're getting a carry from this 4 nibble to the next 4 nibble, then it is called as an auxiliary carry. Right. So you can see after adding this you have 1, this is 1, this is 0, this is 1. So here you will get a 1 bit, and this is a 1 bit where you have a carry for the next. So this carry is called an auxiliary carry. Right. So here you have a 1, and this you have a 1. This is 1, this is 1, this is 1. So here, this is the data which you have got after adding. So this is from D0, D1, D2, D3, D4, D5, D6, and D7. Right. So you are getting a carry from D3 to D4. Here you have got a carry. That carry is called as what? Or auxiliary carry. From one nibble to another nibble, if you are getting a carry, then it is called as an auxiliary carry. Then this auxiliary carry flag will be set. Otherwise, it will be 0. Next, a parity flag. So what is a parity flag? As we know, the parity is used for error detecting and correcting. So whenever I need a data to transmit from one point to another point, I use a parity bit with the data bit. So it indicates that if that parity bit is changed, that means the data which you have sent, which is transmitted from one point to another point, is got corrected, or error, it is having an error. So it indicates that example, I have this is 0, this is 1, this is 1, this is 0. So this is the data which I'm sending. This is D0, D1, D2, and D3. This is the data which I'm sending. Alright. So you can say you have an even number of parity and odd number of parity, where you can indicate the how many bits you are having. Depending upon that, you can design my data whether it is got error or not. So here you can say I'm taking example for even number of ones. If I'm having, I'm making it as 1. So here I can see I have even number of ones, 1 1, it's a 2, 2 is an even. So my parity bit, this is a parity bit which I have made as 1. So this data have transmitted to another end. Right. So when I have transmitted my data into another end, the parity bit have been changed to 0 in case. So it indicates that actually I need to send my data 0110, but it is indicating, the parity bit is indicating as 0. It means my data bit, it may be any bit, it may be a D0 or D1 or D2 or D3, have been changed. Any of the bit have been changed. So that is what my parity bit have been changed from 1 to 0. So depending upon how many number of ones you have here, depending upon that, you're saying you're generating the parity. But see here, if D not have been changed to 1, it means that it's an odd. So it have been made as 0, means the actual data which I need to send is 0110. But what is happening here? It have become, the D note have been changed to 1. So here whenever I'm sending my data from one point to another point, the data will be changed. So that can be find out by using this parity bit. Okay. And next, the zero flag. So zero flag is nothing but this flag will set when my resultant, when my after my ALU operation, if my resultant is equal to 0, right, all the output is 0, it means then my zero flag will be set. Next, sign flag. So, what is a sign flag? So, sign flag, which bit does it indicates the sign is MSB bit, right? Most significant bit. So here, if my sign bit is 0, it means it's in positive. If my sign bit is 1, it means a negative. So sign bit that indicates in the MSB bit. So whenever it is 0, it indicates it's a positive signed, and whenever it is 1, it is a negative. So whenever you are going for signed and unsigned kind of operations, in unsigned kind of operations, you directly operate according to the what operation, like addition or subtraction. Whenever you are going for the signed kind of operation, it means that you go for a two's complement. Like whenever you're going for subtraction, two's complement subtraction or one's complement subtraction, these are done. Complement, by taking some complement subtraction are done whenever you're going for signed numbers. Next, overflow flag. Overflow flag is nothing but if the data is extended more than the capacity, then it means it's an overflow. Next, control flags. So here, the control flags, you can see you have a trap flag, and you have an interrupt flag, and a direction flag. So these are the three flags which you have uh, in a control flag. So here, what is a trap? So a trap is nothing but a single step execution. Right. So here, whenever you are executing any program in the memory location via software, so you have a direct option like run. Right. So run indicates whenever it's nothing but the compiling. Whenever you click on it, you will get the direct result output. Right. Um, Whenever you're taking this trap kind of flags, that is nothing but the single step execution. It means one instruction if it is executed. Suppose I have we can take one example like move ax comma 22, move bx comma 33, and add ax comma bx. Right. So 22 content is present in ax. I'm viewing my registers, which is ax and which is bx. Right. So when you choose the single step execution, when one step is executed, you can see the output, what is happening to the AX register. The second instruction is executed, it means the BX register content is viewed. Next, adding AX comma BX means the addition of BX, the content which is added with AX and stored in AX is shown in the AX. So one after the other, each instruction is executed. You can see the output, what is happening to each instructions. Right, each instruction whenever you're executing. That is what a single step execution. So if you go for a general operation without single step, it means all the instructions which you have will be executed, and directly you can see the output what you're having. So what is a single step execution? It means it a user to execute one instruction at a time. right? So next one is interrupt flag. Interrupt flag is nothing but it is an interrupt enable and disable flag. So what is an interrupt? Interrupt is nothing but what? Stopping the present execution of my microprocessor, right? So whenever I have got an external, this is my microprocessor, whenever I have got an interrupt, external device, you can see external device to execute by my microprocessor. This external device, which is seeing my microprocessor to function, this is called as an interrupt, right? So this will be enabled, this will be made as 1 or 0 when you are having an external device connected to my microprocessor. If my external device is connected, I want to connect to my microprocessor, that means I have got an interrupt, that means this flag will be equal to 1. If I have not connected any external devices to my microprocessor, it means my interrupt flag will be equal to 0, right? And next one is the direction flag. So the direction name itself says we are giving a direction to my register or my memory location. Either I need to increment or either I need to decrement. Right. So, example, I am working with some memory location of 2000. Right. I have some set of instructions. When one instruction is executed, I need to increment the memory location to execute 2001 memory location. Next, I need to execute 2002 memory location. Next, I need to execute 2003. So, my instruction pointer, I need to increment. It means that after executing 2000, I need to increment my pointer to 2001. Next, I need to increment my pointer to 2002 or 2003. Right. So, that to increment my pointer of an source index which I am giving a data, or to decrement my pointer, that is SI, I can decrement from 2003 to 2002 or from 2002 to 2001. I am decrementing my memory location, right? So this is used for SI and DI, source index and destination index. Source index is nothing but we are giving some data, we are giving some data into it by assigning some memory location to SI. And DI is nothing but destination index, where you are looking out the output which is assigned with some memory location. So SI is assigned with 2000, where I can give the input of a string 234, right? And this data I'm sending into the memory location which is in DI, like 1 2 3 4. So DI is assigned with 3000, where I'm seeing my output, and SI is assigned with the memory location 2000, where I'm giving the input. So you can say the direction flag can be used for string operations. Either I need to increment my memory location or either I need to decrement my memory location. So next one is as we have discussed about the execution unit and bus interface unit, you can see this is a pen diagram of my 8086 microprocessor. So actually, so you can see if you see any IC, it will be having with some notch here. This notch which is indicated, where from the left side, the anti-clockwise, you need to count the number of pins, like 1 2 3 4 5 6 7 8 9 10 11 12 20 13 14 15 16 17 18 19 20 21 22 23 24 25 26 till 40. So anti-clockwise, right? So you can see here my as the features which we have said, we have 16 data lines and 20 address lines, and you can say my process working in the minimum mode and maximum mode. So everything will be seen by this pin diagram. So actually our pin, as I said, what is a microprocessor? It's a controlling unit or the ALU which is designed in a very small scale integration, a programmable device. So this is a programmable device, right? So this consists of all the which executes the all the arithmetic and logical operations, and also we can communicate my device via these pins. Okay, here, so you can say the first pin is ground, and the second pin you have a multiplexed and address lines and data lines. So here what you have, how many data lines you have? You have 16 data lines and address lines are 20, right? So data lines you can say from D0 to D15, and address lines are A0 to A90. Right. So instead of using separate pins for address and data lines, we have combined those. So that combining is called as multiplexing. So here, if you see D0 to D15 can be combined with A0 to A15. So it reduces the number of pins which are assigned to this 8086 processor. So you can see AD0 to AD14. Right. So these are multiplexed address and data lines. And next we have NMI, that is an interrupt pin, non-maskable interrupt, and INTR. INTR is nothing but interrupt request. These both are the interrupt pins. Right. And next one is clock, where you how much clock frequency does my 8086 processor works in, 5, 8 and 10 megahertz. Another one is a ground pin you have. And so you can see here, we as we know, my processor works in two modes, minimum mode and maximum mode. So minimum mode is you're connecting for single processor. Maximum mode means more than one processor you're connecting, devices you're connecting to my 8086 processor. So here, whenever you're changing from minimum mode to maximum mode, here the set of pins which you have from 24 to 31 have been changed whenever you're using in the minimum mode and whenever you're using in the maximum mode. Right. So you can see from 28 pin in QS1 is indicated in the minimum mode as INTA. In 25th pin, QS0 is indicated in ALE, address latch enable, and 26 and 27 and 28 S0 and S1 and S2 is indicated by DEN, data enable, data transmit and receive, and memory memory by IO. And here the log is indicated in terms of write signal, and 30 request and grant is indicated by hold acknowledgement, and 31 request grant one is indicated as hold. So these are whenever you are working with the minimum mode, this pins will come into consideration between 31 to 24. Whenever you're working in maximum mode, this set of pins does not come under consideration. These set of pin will be worked in 8086, and remaining you have 40 pin. 40th pin will be a VCC, and 39th pin is an multiplexed address and data, that is nothing but AD15. And here, apart from the multiplexed and address and data lines, we are also multiplexed with the status pins S3, S4, S5, S6 and S7. So why we are multiplexing? The main thing is in order to reduce the number of pins size. Right. So if you're taking all the pins separately, you'll get more than 40. Right. So if the pins are more than 40, the power requirement will be more. So the operation speed will be very less. The circuit will be vast. So these are some kind of points in order to make into consideration whenever you're designing a IC. So in detail, the pin, what is pins? What are the pins which we have, and in detail, what is each pin function? We'll see in the next class. So hope you have understood the what is the definition of my microprocessor, 8086 microprocessor, and what are the characteristics, and what is the internal architecture, and the Venn diagram. Right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.